Hey, welcome back, everyone. Glad you're still with us. We're going to start lecture number 23, beginning our discussion of electricity. I'll say electricity part one. This will this is the beginning of the second third of this course. All right, we'll be going to be discussing electricity and magnetism. Then we'll be talking about waves and some optics, and then finish this section off, the second part of the course, with some understanding of nuclear energy. Okay. Before I begin, I want to do a shout out to my friend Matthew Vergano, who's been checking and making sure I don't make too many errors. So thank you, Matthew, and thank you everyone else who's been helping me out. Um, so today I'm going to talk a bit about electricity. I'm going to tell you a bunch of things you don't know, and just so you know, I'm going to tell you some things that I don't know. Okay, I've been a physicist for almost 50 years, and there's a bunch of things I still don't understand. All right, we're going to talk about electric charge, electric field lines as initiated by Faraday, something called Coulomb's law. You'll see that we've seen something very similar to that, which is another example of an inverse square law. All right, so let's begin with Ben Franklin, the American statesman and inventor and all-around great guy. Everybody knows the story with the kite and the key and learning about electricity. Okay, we all know that electric charge comes in two types. Okay, one we call positive, and the other we call negative. When we think of negative charges, most of us know that these are what we call, one example would be electrons. And an example of a positive particle is called a proton. Okay? So you can have a proton all by itself, you can have an electron all by itself. These are called electric mono means one, electric monopoles. So an example of a positive electric monopole would be a proton. An example of a negative electric monopole would be an electron. Now, why are electrons negative and why are protons positive? Ben Franklin. He randomly chose this nomenclature, okay? The world would not change. Nothing would be different. The laws of physics would be identical if we said positive protons were instead negative, and negative electrons were instead positive. Nothing would change, okay? Now, if you ask me, what is an electron? Well, I can write an equation, relativistic, non-relativistic. I can solve it. I can tell you all different things about electrons, a million things about electrons. But if you ask me what is an electron, the answer is I don't know. And nobody really knows. It's a point particle, really zero dimensions mathematically, with mass and electric charge. So how could something with zero dimension? We don't know. We don't know. So quantum mechanics tries to answer these questions, but when we get right down to it, nobody really knows what an electron is. But we'll use it anyway. We're going to play with it, okay? Now, when we have a plus and a minus, right, we use our imagination. Remember SpongeBob? Our imagination, right? So we're going to use our imagination on what's going on when particles interact. For this, we can thank Faraday. Faraday was one of those really cool scientists long ago who, like many of you, knew absolutely no mathematics. He knew no mathematics. His expertise was doing experiments and measuring things and then writing it down in words. This happens, that happens. There's a force on this magnet, etc. So he did everything in words. Later on, people like Maxwell put these observations to mathematics, and that's what we use today. But Faraday did everything with pictures and with words. So we're going to use some of Faraday's ideas, which are electric field lines. So we're going to imagine that if you have a positive charge, that electric field lines or electric force emanates. Do you know that word? Emanates, okay? Emanates, comes out of a positive charge. Now, of course, there's an infinite number of charges. I can't draw an infinite number of charges. If this had twice the charge, symbolically I would draw twice as many lines, okay? So if you are a positive charge, we imagine that the electric field or force lines come out, are emanating. If you are a negative charge, the opposite is true. We imagine that a negative charge, the field lines, these field lines go in, the electric field lines go into the charge. From infinity, they go in. So here, we would say a positive charge plus charge, we would say is a source of electric field. Here, we would say the negative charge is a sink. Right? Just like water, just like a fluid. It's a sink. The field lines go into a negative and out of a positive. Okay? So let's use these pictures and draw what we imagine happens. Now, it's common knowledge, or everybody pretty much knows, that opposites attract, right? So opposite charges are going to attract. So let's draw a positive charge and let's draw a negative charge. Okay? These lines, remember, emanate out. And they want to keep going to infinity. All right, they want to just keep going. Now, the lines are going out and they say, whoa, check out this really cute negative charge, right? So what happens is they want to go to infinity and say, no, 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 I think I like going there. And so the lines come out, but they go in it. You see how they're they're going into the negative? So these things still come in. We have a picture like this. So this would be attraction, right? A plus and a minus. If you see an exam, I'm going to cross this out, and the charges are not marked. So in other words, if I have a charge like this and a charge like this, I'll call this A and this B, and you see lines that go like this. Notice the arrows. If the arrows are coming out, what does that tell you? It tells you that charge is positive. If the lines are going in, what does that tell you? It tells you this charge is negative. So if there was a multiple choice question that says charge A and B are positive, positive, negative, negative, positive, negative, negative, positive, obviously it would be A is positive, B is negative. Okay? Very simple. All right? All right, so that's a positive and a negative. Let's do two positive charges. Well, once again, there's an old axiom that says opposites attract while the same charges repel. So if I draw a positive charge and I draw a positive charge, once again, the lines come out, right? They're sources. Now, remember, the lines want to go to infinity. They want to keep going. But they see this guy and they say, I don't like him. And this one says, I don't like him. And what happens is you get a picture that looks like this. The lines repel. Once again, if we put A and B here, because the lines are coming out, they're sources, they're both positive charges. So from this picture, we know that A and B are both positive. You see that they repel. What would happen if A and B were both negative? Well, again, negative, negative, repel. How would this picture be different? Do you know? Okay, so here we would say if they're negative, both charges would be sinks. So the lines would go in. Okay, same picture, except the arrows point inward. So once again now we would say A and B, again, they're the same because they're repelling. And because the lines are going in, they're both sinks, so they're both negative. So A and B would be negative. Okay? Fantastic. Now, let's talk about electric charge. Remember, physics, chemistry, these are what we call the hard sciences. So again, if I'm going to talk about this charge pushes on this, and there's a force on these charges, remember, I can't say the force is super big or super small. It's not like psychology. You know, Vlad is really crazy. You know, Ivana is not so crazy. There's no numbers. These are just words, right? In physics and chemistry, we need to put numbers to things. To put numbers to things, to tell us how big or small or what the size of an electric field is, we need to put units on things, okay? So I'm going to tell you about the units of electric charge. Units of electric charge. Okay? Now, an electron, you can't see an electron, it's so small. Okay? And a proton, very, very small. Later, I'll tell you about the size of an atom and things like that. But for now, let's talk about the units. I'm going to use the symbol Q, represents electric charge. Electric charge. I'm going to put a sub P there. Sub P for proton. This is the charge of a proton. I'll write proton for now, okay? The charge, the electric charge on a proton, we know is positive. I'm going to put a positive there. The magnitude of this number, watch this. You don't need to learn this, but it's 1.6, and there's a couple more decimal places, doesn't matter, times 10 to the minus 19th. And the unit of electric charge is called a coulomb. So I'm going to write here, unit of electric charge. Remember, energy is measured in calories or in joules, force was in newtons, and here electric charge is in coulombs. Okay? The charge of an electron is minus, but the magnitude is exactly the same, 1.6 times 10 to the minus 19th coulombs. Notice they would cancel out. So in a hydrogen atom has one proton, one electron. What is the charge of a hydrogen atom? Well, it's the same as the electric charge on all atoms. Atoms are electrically neutral. Electrically neutral means the number of positive charges equals the number of negative charges. So the total charge is 0. Okay? So these are the charges, electron and proton. Notice 10 to the minus 19th. You should be experts on scientific notation now. 0.0, forget it. It's tiny, tiny, tiny. But again, electrons and protons are very tiny. All right? All right, so let's talk about the force between two charges. The electric force. In parentheses, I'm going to write up here, remember Newton's universal law of gravitation. And it was an inverse square law. What does that mean? Remember F of gravity? I said there was a big constant. We didn't have to worry about that, okay? But it was the mass of one times the mass of the other divided by the separation squared. So there's M1, here's M2, okay? And there's the distance between them. If you double the distance, the force becomes 4 times smaller. If you go 10 times farther away, the force is 1/100th, 10 squared. If you go 3 times closer, if your distance is 1/3, when you square 1/3, right, you get 9 times greater. The 1/3 squared comes in the numerator. The electric force is also an inverse square law. This is known as Coulomb's law. So Coulomb's law and Newton's universal law of gravitation are both inverse square laws, okay? Keep that in mind. Inverse square laws. They vary as the square of the distance in the denominator. So I'm going to write F electric equals, just as in the force of gravity, there was a constant here, G, and again, this is not really important. It's only important when I give you to compare forces. This is on the order of about 10 to the minus 11. It's a very tiny constant, 10 to the minus 11. For the electric force, we're going to put a K here. This is the electric constant, some constant. I'll tell you, but it's not important. Now I'm going to write Q1, Q2 over the distance squared. Does everybody see the analogy with Newton's universal law of gravity? Okay, so here, instead of M1, I'll put Q1. Here I'll put D, and here I'll put Q2. Q1, Q2, D. Q1, Q2, D squared. Same form. Here, this electric constant is on the order of 10 to the plus 9. 10 to the plus 9. G was 10 to the minus 11. What's the difference between G, 10 to the minus 11 and 10 to the plus 9? How many steps between them? Well, it's 20 steps, right? Minus 11 to plus 9 is 20 steps. That means 10 to the 20th. So that means, you should know this, that the electric force is so many times greater than the gravitational force. So let's talk for 1 second. I want you to watch. Look, I've been lifting weights. You see, oh, I had a mosquito bite the other day. I thought it was a mussel, but all right. So I've been lifting weights. I've been practicing. So I want you to stay with me. You ready? Okay, here we go. Watch closely because, you know, I may not be very good at this. Ready? Look, I just lifted this eraser. Wow! Do you see how strong I am? Isn't that amazing? Now, how did I lift this? Well, remember, there's a gravitational force between every two particles, right? So there's a gravitational force between every rock, every pebble, every water molecule, every mountain on the Earth. So the entire Earth is pulling on this eraser. And yet, I was able to lift this against the entire gravitational force of the Earth. How could I do that? Well, you can see that I used my muscles. What force am I using when I use my muscles? Well, all you bio people should know that, right, a charged particle in the body called electrolytes, right? And we need ions in our body. That's why you need to ingest sodium and chlorine and potassium, things like that. These charge carriers, as we'll see, are what conduct electricity. So how do my muscles move? My muscles, remember action potential in bio? My muscles move by the electric force, So the electric force in my body is so many times greater in magnitude than the gravitational force. That's why I can lift this, you see? So the weakest force, write this down, the weakest force in the universe is gravity. The electric force is not the strongest, but it's many orders of magnitude greater than the gravitational force. So what kind of problems would you see on an exam with the Coulomb's law? Very similar types of problems as that we had for Newton's law of gravity. If you double each charge and halve the distance, what happens to the electric force? So I'll write this down. Double each charge if both charges are doubled while the separation is halved. What happens to the electric force, to F electric? Okay, so let's see. F electric equals, forget the K, okay? So it goes like, forget the K. So I'm going to make this, instead of Q1 and Q2, I'm going to double each charge. So Q1 becomes 2Q1, Q2 becomes 2Q2. And what am I doing to the distance? Instead of D, I'm making it 1/2 D, but then I have to square it. So in the numerator, I have 2 times 2 is 4, divided by 1/4. And so the answer is 16 times greater. Okay? So this would be the type of problem that I would ask on Coulomb's law. All right? Double the charges, halve the charges, etc., etc. Good. Very good. Okay. All right. I'll end this lecture here. And in the next lecture, we'll start talking about what electrical conductors are, what electric insulators are, and we'll get more into the nitty-gritty of electricity and magnitude. All right? So, good. See you next time. Take care.